So we know what photogrammetry is, or at least how it's defined, and that's about as far as we're going to go with that tonight. Before I go on, I need to just mention that we're about to review some concepts that are absolutely crucial to everything that we're going to do for the rest of the quarter as far as computations and calculations and understanding some concepts. In a class of 12 to 16, there's always going to be a couple that look at this and say, yeah, so what's the point? That's easy. There's going to be some people who are going to watch this and just decide that they need to run screaming from the class. And most people are going to fall somewhere in between. We're going to talk about math, trigonometry, and review some other concepts, especially talking about spreadsheets. If you have a problem with the trigonometry, especially, there's a supplemental video on trigonometry. If you aren't really up to speed on spreadsheets, there is a supplemental video on spreadsheets. Don't give up until you watch those videos, and if you still have a serious problem, then let's talk. I am committed to making this class doable by everybody. If, however, you've never used a spreadsheet, don't even know what it is, there may be a problem. So watch these things as I talk about the math. If you can do the following math in a spreadsheet, skip the spreadsheet video. If everything, even if you don't understand the math, if I could explain it to you, you would know how to do it in a spreadsheet, then skip that. If you if you understand what I'm about to say with regard to trigonometry, you can skip that. If it's a little fuzzy, then you'll want to go back. First of all, let me say that photogrammetry is all about ratios. One of the things about ratios is it's going to deal heavily with conversions, unit conversions. Now, here's a conversion that doesn't make sense and isn't important. Why, when they were deciding what distances were important, did they come up with a chain as being 66 feet? And did you realize that a mile? What is a mile? It's 80 chains. What's an acre? That's 10 square chains. You don't need to know that. But if you could do some these conversions in a spreadsheet, just a reminder kind of where we're going. A little more important, understand that there are different kinds of feet and meters, and you as a geomatics professional in the United States are going to have to understand there's a difference between an international foot, which is nicely rounded off to 0.3048 meters exactly. That's the definition. However, if you've got a U.S. survey foot, not so even, but it defines that 39.37 inches exactly is 1 meter. So just understand that there are differences here. When we get into projections, this is going to be the least of our worries, but just understand that there are differences here. As we start to talk about angles, that there are components to angles. Very often we are going to work with decimal degrees, 38.457 degrees. But degrees are measured, especially when you think of in geodetic terms. You got degrees, minutes, and seconds. Just understand that there's 60 minutes in a degree, which would mean 3,600 seconds, because 1 minute is 60 seconds. A radian. I'm not going to go into the definition of a radian, but just understand that 1 radian is 180 degrees. That is, it's actually 180 degrees divided by pi. Pi, you hit your calculator and it's just a number. Pi is just a number. So, if you want a radian, 180 degrees divided by pi. If you could convert degrees into radians, or vice versa, using a spreadsheet, either using the degrees function or using the math, and dividing or multiplying as necessary. There's another form of angular measurement called grads. For a while it was known as gons. It may still be in some circles. That just divides that 180 degrees into 200 units, so it's a little bit more even. It was used very heavily in photogrammetry, but I'm not going to impose that on anybody else. And finally, understand that 100 grads, 90 degrees is a right angle. Two lines that are perpendicular to each other meet at a right angle or 90 degrees. A circle is 360 degrees or 2 pi radians. So the radians is really important because if you are dealing with a calculator or a spreadsheet or a computer, if you are programming a computer, the computer is going to work in radians and it's always going to have to be converted. The natural output of a computer, if you compute an angle, is probably going to be radians. Most calculators have a switch that you can flip it over to degrees, but just understand that idea that when you get an answer, you may be getting radians and you may need to convert those radians to degrees to answer a question. Getting back to ratios, unit conversions are a good example of ratios that we've already mentioned. In this class, it's primarily going to be between centimeters, microns, meters, and inches and feet, between metric and standard units. Scale is represented very often as a ratio. It could be 100 feet per inch, also known as 1 inch equals 100 feet. It could be a unitless representative fraction, 1 to 1200. 1 inch is 100 feet. 12 inches in a foot. 12 times 100 gives us that 1 to 1200 as the representative fraction. One hand is 1200 hands. 1 foot on a map is 1200 feet. 1 fingernail on the map is 1200 fingernails in real life. So we've got that unitless fraction. The internal geometry of a photograph. We're going to spend a lot of time talking about the internal geometry of photography and the ratios. Won't go into detail here, but understand that what happens inside the camera is a representation of what happens outside the camera in real space, and those measurements are expressed in ratios. And finally, trigonometry. Trigonometry with respect to a unit circle, a cosine being the x in the unit circle, the sine being a y. And what that really means is that if we take that unit circle, radius of 1, wherever the angle, we've got an angular measurement, that line strikes a circle. The cosine and sine are defined as the x and y. that would form a right triangle wherever T, which intersects the circle, and then to the X and Y axis. So from angle T, you go out, you intersect the unit circle. The X value of that point is the cosine. The Y value of that point is the sine. So what that means is that the sine, cosine, and tangent can actually be expressed as ratios of the sides with respect to the angle in question. So if we were to form a triangle there at angle T, from the origin you go out X, the certain number of units in X, and then you go up perpendicular, certain number of units in Y, and you end up at that point. That ratio, X over 1, Y over 1, are the ratios that are going to hold for that triangle, no matter how big the triangle gets. So what we're saying is, if we were to form a triangle based on that angle, the sine is the ratio of the opposite side over the hypotenuse. The cosine is the ratio of the adjacent side over the hypotenuse. The tangent is the ratio of the opposite over the adjacent. There's a cute story out there somewhere, if you can find it. It talks about a Native American tribe called the Sokotoa, and the story goes that they always built their teepees in right angles, and there's a long story, but basically Sokotoa, S-O-H-C-A-H-T-O-A, is a good way to remember those relationships. Trigonometry. The sine is just a number. If you've got a side and you've got another side, you can divide them and you're going to get the sine. If you've got the angle, you can punch in the angle to the calculator, get the sine, and then use it to compute missing sides. As far as concept review, the algebra, some things that we'll need to understand. Order of operations. If you could put this equation into a spreadsheet and evaluate it and get the correct answer, then you understand everything, I would say everything you need to know about spreadsheets. If it would take you multiple steps, multiple cells, that's fine. But you ought to be able to evaluate this expression in a spreadsheet. Order of operations, simply saying that we're going to do everything inside parentheses first. So in this case, you would do the 2 times 5 would be one of the first things that you do. We're going to simplify exponents, working from left to right. That next parenthesis involves an exponent, so we've got to simplify that 3 to the 4th power. Divide by 9, that would solve the that parenthesis. So we've got 8 plus the result of 2 times 10 times the result of 3 to the 4th divided by 9. The 2 times 10 would be multiplied by the other parenthesis first before it's added to 8, because multiplication is done before additions and subtractions. So if you understand order of operations, if you could do that in a spreadsheet, you're well on the way. If not, then you'll definitely want to spend some time during one of the office hour labs getting caught up on that. A little bit of trig, a little bit of algebra, some fairly simple. This is an explanation of the Pythagorean theorem. Not going to explain the whole thing. Just understand that this is a fact, that if you have a right triangle with sides A and B and a hypotenuse C, a squared plus b squared equals c squared. That's just a fact. If you have A and B, then you can solve for C. Solving for C, also known as the distance formula. We'll understand why later as we start talking about coordinates. But here again, if you could take, if I told you that A is 4 and B is 7, and you could raise A to the second power, A squared, B to the second power, B squared, add those two things, and then take the square root of the result in a spreadsheet, you've gone a long way towards understanding spreadsheets. You don't really have to understand least squares, but we will touch on this a couple of times. Just understand the idea of least squares and the concept that there's no such thing as a perfect measurement. I could take any two of those points and connect them and have a line segment. The problem is the true line exists out there somewhere. Measurements based on their precision are going to fall within a certain tolerance of the line. They won't be perfect. The more measurements we have, the more redundancy we have. Solving for redundant solutions is what least squares is all about. Just to well, we won't even state what least squares is. It just comes down to minimizing the error at every point, coming up with the most likely line to fit the measurements that are out there. Some of the softwares that we are going to get into, we're going to do some image manipulation. If you know Photoshop, that's fine. I use GIMP. We will have GIMP installed on all the computers. It's open source. There will be a portable version available that you don't even have to install. You can run it off a USB key if you want to. It's extremely powerful, open source, and all the examples that I give and everything that I do is going to be in GIMP. You are free to use anything that you want. If it's Photoshop, if it's Paint.net, GIMP, you decide, as long as you can do the actions you need to do. Spreadsheets, I've mentioned before, they are the absolute best replacement for programming. It's as close to programming as you're going to get within an application environment. If you like Excel, that's great. It's that's all fine. Give me Excel files. I am going to work in OpenOffice. Once again, a free and open source alternative. It's what I like. I'll have an installable version and a portable version for you to use if you choose to use those at home. They will also be installed on the computers.